Our universe began not with a slow burn, but a violent, impossible growth spurt. In the first fleeting fraction of a second after the Big Bang, space itself expanded faster than the speed of light. This was the cosmic inflation era, a blink of cosmic time that set the stage for every galaxy, star, and planet we see today. Yet this monumental event is shrouded in deep mystery. By the end of this exploration, you will understand the 25 grand puzzles that this inflationary moment left for us to solve. We will confront what could have triggered such a fantastic expansion and ask if our entire cosmos is just one bubble in an infinite multiverse. Which fundamental cosmic mystery do you find most compelling? That initial burst of cosmic expansion presents us with our first and perhaps most profound mystery. What flicked the switch to begin with? What specific set of conditions could command the very fabric of space to stretch so violently and so fast? The leading theoretical answer points to something called the inflaton field. Think of this not as a physical thing you can touch, but as an invisible energy field that saturated all of existence in that first fleeting moment. It is a hypothetical scalar field, which in simpler terms means its value could vary from point to point, much like temperature changes across a room. In the peculiar physics of the early universe, this field possessed a bizarre property. It generated a form of repulsive gravity. Instead of pulling things together, this energy pushed space apart, and it did so with unimaginable force, driving that exponential expansion we call inflation. Yet the true identity of this inflaton field remains completely unknown. We do not know what it is made of, how it emerged, or what specific rule caused it to activate. It is the ghost in the cosmic machine, a theoretical necessity that explains so much of what we see, while itself remaining one of cosmology's deepest enigmas. The trigger, the very first cause, is still missing. This violent expansion could not last forever, and the mechanism that shut it down is our second great mystery. We call this the graceful exit problem. How did the universe transition from that cold, stretched out void of inflation into the hot, dense, particle-filled chaos of the classic Big Bang? The process is known as reheating, and it is as dramatic as it is poorly understood. Picture the inflaton field as a vast, tranquil lake perched high on a mountain. This position represents the energy that drove inflation. For the expansion to stop, this field had to roll down the mountain, so to speak, losing its immense potential energy. But where did that energy go? It had to be transferred, and transferred efficiently into something else. That something else was matter and radiation. The energy stored in the inflaton field was converted, through a process we can only theorize about, into a seething hot soup of fundamental particles and light, instantly heating the frozen universe to unimaginable temperatures. This was the moment the Big Bang, as we traditionally picture it, truly began. Yet we do not understand the precise mechanics of this energy transfer. Was it a smooth roll downhill, or a sudden, violent drop? Did the field oscillate and decay, shaking its energy loose like a tree shedding fruit in a storm? The details of this transition are critical. If it happened too efficiently, the universe might have collapsed back on itself immediately. If it was too inefficient, matter might never have properly formed. The graceful exit had to be, as the name implies, just right. And the mystery of how that happened, how the inflaton field dissipated to create the very particles we are made from, remains one of the most pivotal unanswered questions in all of cosmology. But what if we could actually hear the echoes of that violent birth? This leads us to a third and thrilling cosmic mystery, the hunt for primordial gravitational waves. These are not sound waves, but literal ripples in the fabric of spacetime itself, generated by the most violent tremors of the inflationary expansion. Think of the infant universe as a vast, turbulent ocean. The sudden, incredible stretching of space during inflation would have sent powerful shudders through this cosmic ocean, creating waves that have been traveling for almost 14 billion years. Finding these waves would be the ultimate smoking gun for inflation, a direct recording of the event itself. The challenge is that these signals are incredibly faint, a whisper buried under a cacophony of cosmic noise. Projects like the BICEP experiment, located at the South Pole, stare at the most ancient light we can see, the cosmic microwave background. They search for a specific twisted pattern in that light, a unique signature that could only have been imprinted by these primordial gravitational waves. Yet the universe is a messy place. The signal they seek is obscured by a more local contaminant, interstellar dust within our own galaxy. This dust can create a similar twisted pattern, mimicking the very signal scientists are desperate to find. It is like trying to hear a single, quiet note from a symphony performed at the dawn of time, while a loud rock band is playing right next to you. Distinguishing the true cosmic signal from this dusty foreground is one of the greatest technical challenges in modern cosmology. The prize, however, is immeasurable. Detecting these primordial ripples would not just confirm inflation, it would allow us to listen to the very first vibrations of reality. These faint quantum whispers from the beginning of time are the very reason you exist. Every galaxy, every star, every planet traces its ultimate origin back to a ghostly imprint laid down during inflation. This is our fourth mystery, the origin of cosmic structure itself. In the strange world of quantum physics, complete emptiness is impossible. Even in a perfect vacuum, there are tiny, fleeting fluctuations, particles, and energy popping in and out of existence. During the unimaginably dense first moments, the inflaton field was also subject to these quantum jitters. It had tiny, random variations in its value across different points in space. Under normal circumstances, these fluctuations would be far too small to matter, vanishing as quickly as they appeared. But inflation acted like a cosmic amplifier, stretching these subatomic wrinkles to astronomical proportions. A quantum blip that was once smaller than a single proton was suddenly inflated to a scale larger than our observable universe. These stretched out ripples in the inflaton field became imprinted as tiny differences in the density of matter and energy. Where the field was slightly more dense, a bit more matter would eventually coalesce. Where it was slightly less dense, a void would form. These minute differences, frozen in the fabric of the cosmos, became the gravitational seeds for everything that followed. Over billions of years, gravity pulled matter toward these slightly denser spots. They grew into the first stars, the first galaxies, and the vast cosmic web we see mapped across the sky today. Yet a profound puzzle remains. Why did these initial quantum fluctuations have the exact statistical properties they did? The pattern of these seeds was incredibly specific, a nearly perfect set of random variations that allowed for the formation of a rich and structured universe, but one that is not so lumpy that it immediately collapses into black holes. It was a Goldilocks arrangement, perfectly balanced to produce a cosmos capable of hosting galaxies and life. We can observe the result of this pattern in the cosmic microwave background, the afterglow of the Big Bang, which shows a remarkably consistent temperature across the entire sky, dotted with the tiny variations that became our world. But we do not know why the quantum rules of the early universe conspired to produce this particular, fruitful pattern, and not another. The origin of this specific blueprint for all existence remains one of the most fundamental and unanswered questions in science. That remarkably consistent temperature across the cosmos presents a puzzle so deep it nearly broke the Big Bang theory. Why does the universe look the same in every direction? This is the horizon problem. For two distant regions of space to have the same temperature, they must have once been close enough to exchange heat, to reach a thermal equilibrium, just like 2 cups of coffee in the same room will eventually cool to the same temperature. But in the standard Big Bang model without inflation, there simply hasn't been enough time since the beginning for light, or any form of information, to have traveled between these far-flung points. They are beyond each other's cosmic horizons, forever out of touch. How then did they coordinate to have the exact same properties? It is as if you met a perfect stranger on the other side of the world who was wearing the same clothes, had the same haircut, and was humming the same song as you without any prior communication. This seems impossible. Cosmic inflation provides an elegant and powerful solution. It suggests that the entire observable universe, from one end to the other, was once crammed into a tiny subatomic region. This minuscule speck was so small that every part of it was in intimate contact, easily swapping energy, and settling into a uniform temperature. Then, in a flash, inflation blew this tiny, connected region up to a size larger than our entire visible cosmos. The uniformity was baked in from the start, and then simply stretched across the sky. The problem is not that the universe is uniform, but that our perspective has grown so vast. We are looking at a single, stretched-out fingerprint from the dawn of time. The ongoing quest is to find definitive proof of this mechanism. While inflation perfectly explains the uniformity we see, scientists are searching for subtle imprints in the cosmic microwave background that would confirm the universe was once that tiny, connected seed. They look for specific patterns that could not have been created by any other process. Finding that evidence would not just solve the horizon problem, it would confirm that our entire cosmic history was written on a subatomic scale. This incredible uniformity is matched by another cosmic coincidence, a geometric perfection that seems almost too good to be true. The shape of our universe, on its largest scales, is astoundingly flat. This is the flatness problem, and it is one of the most telling clues about our cosmic origins. To understand this, picture space itself having a shape. It could be positively curved, like the surface of a sphere, where parallel lines eventually meet. It could be negatively curved, like a saddle, where parallel lines diverge. Or it could be perfectly flat, like a vast, infinite sheet of paper. For the universe to be flat, the precise balance between the expansion energy and the pull of gravity had to be perfectly, exquisitely tuned from the very first moment. Even a tiny deviation from this perfect balance in the early universe would have been magnified over billions of years. If there had been a little too much matter and gravity, the universe would have collapsed back on itself long ago in a fiery big crunch. If there had been a little too much expansion energy, the universe would have flown apart so rapidly that galaxies and stars could never have formed. The fact that we see a universe that is still expanding, yet filled with structure, means the initial conditions were balanced on a knife's edge. It is like rolling a ball down a hill with the goal of having it come to a stop on a single, specific blade of grass after traveling for miles. The odds seem impossibly low. Cosmic inflation provides a powerful and elegant explanation for this fine-tuning. Think of the universe before inflation as a small, wrinkled sphere. No matter how curved its surface was initially, The violent, exponential stretching of space during inflation would have smoothed it out, just as blowing up a balloon makes a small section of its surface appear much flatter. Inflation drives the universe toward geometric perfection, relentlessly ironing out any curvature. This is why our measurements of the cosmic microwave background show a universe that is flat to within a margin of error of just 1%. Yet, this very success raises a new and profound question. Is the universe perfectly flat, or only nearly so? Our most precise observations suggest a flat geometry, but could there be a subtle residual curvature that our instruments have not yet detected? If the universe is perfectly flat, it has profound implications, suggesting it may be truly infinite in extent. If it has even the tiniest curvature, it would be a finite, closed cosmos. The debate is not settled. The quest to measure the geometry of the universe with ever greater precision is one of the central goals of modern cosmology, because the answer holds the key to understanding the ultimate fate of everything and the true nature of that first, fleeting moment of creation. Our universe's perfect flatness is matched by another profound absence, a ghost from the dawn of time that should be everywhere but is nowhere to be found. This is the mystery of the missing magnetic monopoles. In our everyday world, magnets always come with two poles, a north and a south. You can break a bar magnet in half, but you will only get two smaller magnets, each with its own north and south. A magnetic monopole would be a fundamental particle that is just a north or just a south, a solitary magnetic charge. Grand unified theories, which attempt to merge the electromagnetic, weak, and strong nuclear forces into one, strongly predict that these bizarre particles should have been forged in the incredible heat of the very early universe. They would be incredibly heavy, stable, and practically indestructible. If they were created, they should still be here today, a cosmic relic as common as protons. We should be tripping over them. Yet, despite decades of searching, not a single confirmed magnetic monopole has ever been found. They have vanished without a trace. So where did they all go? Cosmic inflation provides a compelling, almost poetic answer. Think of the monopoles as a dense crowd of people packed into a tiny room. Inflation is like suddenly expanding that room to the size of the entire observable universe. The crowd is stretched so thin that the average distance between any two people becomes astronomically vast. Inflation did not destroy the monopoles. It simply diluted them. It spread them out so incredibly thinly across the cosmos that the chance of one ever wandering into our detectors becomes almost zero. This is a brilliant solution, but it forces us to confront a deeper question. Is this dilution the real answer, or is it a convenient way to explain away a failed prediction? Perhaps monopoles never existed at all. Maybe our grand unified theories are pointing in the wrong direction, or the conditions for their creation were never met. The empty silence from our experiments is a powerful reminder that the universe often defies our most elegant ideas, forcing us to look deeper into the strange physics of that first fantastic moment. This overwhelming dilution of monopoles hints at a cosmos far grander and stranger than we ever imagined. If inflation could stretch our universe so thin, what is to stop it from happening again, elsewhere? This leads us directly to one of the most mind-bending concepts in all of science, the multiverse hypothesis. The theory of eternal inflation suggests that the process that created our universe may not be a one-time event, but an endless, self-replicating phenomenon. Picture the inflaton field not as a single event that started and stopped, but as an infinite, bubbling ocean. In most of this ocean, inflation is forever ongoing, stretching space at an unbelievable rate. But here and there, like bubbles forming in a boiling pot, pockets of the field undergo their own graceful exit. Each of these bubbles stops inflating internally, creating a hot, dense universe like our own, while the space outside of it continues to inflate at a fantastic speed. The result is a vast, ever-growing cosmic foam, where each bubble is a separate universe, forever isolated from the others. The truly staggering implication is that the fundamental laws of physics, the constants that dictate how particles interact and forces behave, might be set randomly during each bubble's formation. In this infinite tapestry, every conceivable set of physical laws would be realized somewhere. There would be universes where gravity is repulsive, universes where atoms cannot form, and perhaps a rare, precious few where the constants are perfectly tuned, as if by chance, for the emergence of stars, planets, and life. This idea forces us to confront a profound question. Are the laws of our universe fundamental and necessary, or are they merely a local, accidental byproduct of our cosmic address? The multiverse could explain the apparent fine-tuning we observe without the need for a designer, simply through the sheer statistics of infinite variety. Yet, this leads to a major scientific crisis. If these other universes are permanently beyond our observational horizon, causally disconnected from us forever, how can we ever test this idea? Does the multiverse belong to the realm of testable science, or has it crossed into untestable metaphysics? Some physicists propose that a collision between two of these bubble universes in the distant past might have left a scar on our cosmic microwave background, an anomalous pattern we could one day detect. Others suggest that the very nature of the quantum fluctuations that seeded our galaxies might hold a fingerprint of our multiversal origins. For now, the evidence remains elusive. The multiverse hypothesis stands as a breathtaking possibility, a logical extension of our best theories that challenges not only our place in the cosmos, but the very definition of what science can ultimately explain. The infinite multiverse offers a dizzying answer to where we are, but it only pushes the ultimate question one step further back. What happened before the very first bubble? We now confront the most profound mystery of all, the nature of the initial singularity and the reality of a beginning. Our entire story of cosmic inflation starts with a trigger, a flick of a switch in the first fraction of a second. But what was there before that switch was flicked? The equations of general relativity, when rewound to time zero, predict a singularity, a point of infinite density and temperature where the known laws of physics simply break down. It is the ultimate edge of our understanding, a mathematical warning sign that our theories are incomplete. For a long time, this singularity was considered the absolute beginning, the moment where time itself was created. Yet many cosmologists now question this stark conclusion. Could inflation be not the start of everything, but merely a dramatic phase in a much longer, perhaps eternal, cosmic story? One compelling alternative is the concept of a big bounce. Imagine a previous universe, not unlike our own, that expanded to a maximum size and then, under the pull of gravity, began to contract. It would have collapsed down, not to a true singularity, but to an incredibly hot, dense state. At that moment of maximum compression, the laws of quantum gravity, which we do not yet fully understand, could have caused a cosmic rebound. Instead of crushing itself out of existence, this previous universe would have bounced, with the immense energy of the collapse fueling the violent expansion we call inflation. In this view, our Big Bang was not a birth from nothing, but a spectacular rebirth from the ashes of a prior cosmos. This cyclical model of the universe, of endless expansion and contraction, elegantly sidesteps the philosophical problem of a definitive beginning. But the evidence remains elusive. If a previous universe existed, did it leave any trace, any cosmic memory imprinted on our own? Some theories suggest that the precise pattern of the primordial gravitational waves we search for could carry a faint echo of the pre-bounce era, a whisper from a time before our time. Others propose that the very nature of the initial quantum fluctuations could reveal whether space-time has always existed. The challenge is monumental, as the incredible heat and density of the bounce would have likely scrambled any detailed information from the prior cycle. We are left staring into the first moment, wondering if we are seeing the ultimate genesis or simply the latest chapter in an infinite book. Did time have a true beginning, or has the cosmos always been, transforming itself through endless cycles of death and renewal? This is the final frontier of cosmology, the quest to understand what, if anything, came before the beginning we think we know. This very infinity that defines the multiverse creates a crisis for prediction. If every possible event happens an infinite number of times across an endless sea of bubble universes, then what does it even mean for something to be likely or unlikely? This is the measure problem, a deep mathematical and philosophical puzzle that threatens to undermine the predictive power of eternal inflation itself. Imagine you are trying to count the number of planets that host intelligent life. In an infinite multiverse, there are an infinite number of planets with life, and also an infinite number of barren, lifeless worlds. How do you compare these two infinities to decide if life is common or rare? Simply put, infinity divided by infinity is not a number. It is an undefined mathematical operation. Without a way to carefully define a proportion, to create a cosmic census, we cannot say anything meaningful about probabilities. The theory loses its ability to make testable predictions about our own universe. Why, for instance, do we observe a cosmological constant with a specific tiny value? In an infinite multiverse, there should be countless bubbles where this value is much larger, and countless others where it is negative. Without a proper measure, we cannot calculate whether our observed value is statistically expected or an astronomically improbable fluke. Scientists have proposed various mathematical techniques to impose a measure, to essentially draw a finite box around a portion of the infinite multiverse and count what is inside. But different ways of drawing this box yield wildly different answers. One counting method might suggest our universe is typical, while another would render it virtually impossible. The core of the problem is that we lack a fundamental principle from physics to tell us which counting method is correct. The measure problem is not just a technicality. It strikes at the heart of whether the multiverse can ever be a scientific theory. If it cannot generate firm, testable probabilities for what we should observe, then does it truly explain anything at all? Or does it merely suggest that everything that can happen does happen somewhere for no particular reason? Solving this puzzle requires a deeper understanding of infinity itself, and perhaps a new kind of mathematics that can tame the chaotic possibilities of an eternally inflating cosmos. This staggering fine-tuning of the universe pales in comparison to a numerical mismatch, so vast it threatens to unravel our entire understanding of physics. We are confronted with the cosmological constant problem, arguably the most severe discrepancy in all of modern science. The energy of empty space is not zero. Modern cosmology reveals that the vacuum of space itself possesses a faint, repulsive energy, a force we call dark energy, which is causing the expansion of the universe to accelerate. We can measure the strength of this energy by observing distant galaxies. Its value is incredibly small, but it is definitely not zero. This measured value is the cosmological constant. Now, let us rewind to the cosmic inflation era. According to our best theories of quantum physics, the vacuum during that period should have been screaming with an unimaginably dense energy. Every cubic centimeter of space would have been packed with a seething, violent activity of virtual particles popping in and out of existence. When we calculate the theoretical energy density of this quantum vacuum during inflation, we arrive at a number. Then we look at the energy density we measure in today's universe. The two numbers should be somewhat related, remnants of the same fundamental physics. But they are not just different. They are separated by a factor of 10 followed by 120 zeros. This is a 1 with 120 zeros after it. To grasp the scale of this error, it is the difference between the energy released by a single nuclear explosion and the energy required to power a single thought in your brain. It is the most spectacular failure of a theoretical prediction in the history of human thought. How can our two most powerful and successful theories, quantum field theory and general relativity, be so catastrophically wrong about the energy of nothing? The vacuum energy predicted by quantum mechanics is like a theoretical ocean, trillions of light years deep, raging with power. The cosmological constant we observe is the faint, still dampness on a single grain of sand on the shore of that ocean. This is not a small adjustment. This is a sign that something fundamental is missing from our picture of reality. Perhaps the inflaton field and its energy are not the same as the quantum vacuum energy we calculate. Maybe some mysterious yet unknown symmetry of nature forces most of that vacuum energy to cancel itself out, leaving behind only the tiny whisper we detect today. Or could the multiverse provide an answer? In an infinite landscape of bubbles, perhaps only in those exceedingly rare universes where the cosmological constant is almost zero can galaxies ever form and life emerge. We would, of course, find ourselves in such a bubble, a statistical fluke in a cosmos mostly hostile to our existence. Yet this feels to many like a philosophical surrender. The cosmological constant problem stands as a silent monument to our ignorance, a glaring signal that until we can reconcile the quantum world with the force of gravity, a true theory of everything will remain just beyond our grasp. This fine-tuning crisis points to an even deeper layer of uncertainty, one that strikes at the very limits of our knowledge. The seeds for all cosmic structure were born as quantum fluctuations, tiny jitters on scales far smaller than a single atom. Inflation then stretched these microscopic wrinkles to astronomical sizes. But here lies the trans-Planckian problem. To create the patterns we see in the cosmic microwave background, inflation must have stretched fluctuations that were originally smaller than the Planck length. This is the shortest possible meaningful distance in the universe, a scale so tiny that the very concepts of space and time lose their meaning. At this scale, the smooth geometry described by general relativity shatters, and we enter the unknown realm of quantum gravity. Our current laws of physics simply break down. We have no theory to describe what happens there. This creates a profound dilemma. The entire story of cosmic structure relies on extrapolating our known quantum physics into a territory where it is almost certainly wrong. It is as if we are trying to understand the origin of a magnificent oak tree by studying the properties of a fully grown forest. We are missing the physics of the seed itself. The character of those initial quantum jitters, the very blueprint for galaxies, might have been fundamentally altered by effects we cannot yet comprehend. Perhaps space-time is not continuous but granular at that scale. like a digital image pixelating when you zoom in too far. Maybe vibrating strings from string theory dictated the initial vibrations. The unsettling truth is that the specific pattern of hot and cold spots we observe in the ancient sky, the one that gave rise to our Milky Way, might be an accidental byproduct of unknown physics operating at the absolute edge of reality. The trans-Planckian problem forces us to admit that our most successful cosmological story may be built on a foundation we have not yet discovered. This precise calibration of the universe's expansion points toward an even more fundamental puzzle, one written into the very laws of physics. Why do the fundamental constants have the exact values they do? The inflaton field itself was governed by specific parameters, a kind of cosmic recipe that included its mass and how strongly it interacted with other fields. Alter any one of these numbers by even a minuscule amount, and the entire story of our universe changes dramatically. If the inflaton's energy had dropped too quickly, inflation would have ended almost instantly, leaving no time to smooth out the cosmos or plant the seeds for galaxies. If it had rolled too slowly, inflation would have continued forever, stretching space into an eternal, cold, and empty void. The strength of the quantum fluctuations, the duration of the expansion, the success of the graceful exit, every single step relied on a set of numerical values that appear perfectly chosen for a single outcome, a universe that can eventually host life. This is the fine-tuning problem in its most stark form. It feels as though a vast cosmic dial was set with impossible precision. The odds of randomly landing on this specific combination of numbers from all the possible values seem astronomically low, almost as if the universe knew we were coming. So how do we explain this incredible luck? One controversial answer emerges directly from the multiverse. If an infinite number of bubble universes exist, each with its own randomly selected set of physical constants, then it is no surprise that we find ourselves in one of the rare habitable ones. In a cosmos where the laws of physics are a lottery, we are the lucky winners. This line of reasoning is known as the anthropic principle, the simple idea that our observations of the universe must be compatible with our existence as conscious observers. We could not possibly find ourselves in a universe that prohibits life. While this logic seems inescapable, it leaves many scientists deeply unsatisfied. Does the anthropic principle truly explain anything, or does it simply redefine the mystery? It risks shutting down further inquiry by attributing the universe's order to a statistical fluke within an unobservable reality. The quest for a deeper answer continues, a search for a true theory of everything that might one day derive these constants from first principles, showing that they could not have been any other way. Until then, the specific numbers that guided our cosmic dawn remain a silent, profound question mark. That cosmic blueprint for all structure, the pattern of hot and cold spots in the ancient light, holds a deeper secret than its mere arrangement. The statistics of these fluctuations, the mathematical rules governing their distribution, are just as important as the pattern itself. Most simple models of inflation predict that these primordial seeds should follow what is called a Gaussian distribution. This is a very specific, bell curve kind of randomness where the fluctuations are completely random and independent of one another. There are no hidden correlations or unexpected shapes. It is the statistical signature of a quiet, non-interacting field. But what if the early universe was not so quiet? The search is now on for subtle deviations from this perfect randomness, features known as non-Gaussianities. Finding them would be like discovering that the static on an old television screen contains faint, ghostly images. These statistical anomalies would be a direct fingerprint of the inflaton field's personality, revealing that it was not a solitary, serene entity, but a dynamic player interacting with itself or with other yet unknown fields. A perfectly Gaussian pattern suggests a very simple, minimal kind of inflation. But if we find even a hint of non-Gaussianity, it would immediately rule out those simple models and force us to consider a much richer and more complex drama in the first moments. It would tell us that the inflaton field had a more intricate life, that it bumped into other forces, or that its energy landscape was not a smooth, gentle slope, but a terrain with cliffs and valleys. This is not just a minor statistical quirk. It is a crucial key that could unlock the specific physics of inflation, telling us not just that it happened, but exactly how it happened. The hunt for this statistical ghost in the cosmic data is one of the most active and exciting frontiers in cosmology, a quest to read the hidden diary of the inflaton field itself. While we ponder the subtle statistics of the universe's birth, a far more dramatic possibility lurks within the vacuum of space itself. The stability of our entire cosmos might be an illusion. This is the chilling mystery of the false vacuum. Our universe appears to be in a stable state, with empty space possessing a certain low energy level. But what if this is not the true lowest possible energy state? What if our vacuum is merely metastable, perched precariously on a cosmic ledge, like a ball resting in a small dip on the side of a much larger hill? This seemingly stable position is called a false vacuum. The true vacuum, the absolute bottom of the cosmic energy hill, could lie far below us. The terrifying implication is that our universe could, at any moment, undergo a process called vacuum decay. Through a quantum tunneling effect, a tiny bubble of this true, lower energy vacuum could spontaneously form somewhere in space. The laws of physics inside this bubble would be completely different, and the walls of the bubble would expand outward at nearly the speed of light. This would not be an explosion in space, but an explosion of space itself, a fundamental rewriting of reality. Every fundamental force, every particle, every law of physics would be irrevocably altered in its wake. The bubble would expand forever, erasing the universe as we know it, and replacing it with something utterly alien and unrecognizable. There would be no warning and no escape. The process would be triggered not by anything we could predict, but by a random quantum event, or perhaps by a high-energy experiment concentrating enough force in one place to punch a hole through the false vacuum floor. This connects back directly to the very beginning, to the inflationary vacuum itself, the inflaton field that drove the universe's fantastic expansion had to eventually decay, to roll down its energy hill and heat the universe. Our current vacuum is the state it settled into. But if that settlement was not into the true minimum, but only a temporary resting place, then the entire cosmic story that followed, the rise of galaxies and life, is nothing more than a beautiful, temporary structure built on a foundation that could vanish in an instant. The fate of the false vacuum forces us to ask a haunting question. Is our reality fundamentally stable, or are we just living on borrowed time in a cosmic waiting room, unaware that the true nature of existence is yet to be revealed? This profound instability in the vacuum is mirrored by a fundamental imbalance woven into the very substance of our existence. Every single thing you see, from the screen in front of you to the most distant star, is made of matter. But our most fundamental theories insist that the Big Bang should have created equal amounts of matter and antimatter. When a particle of matter meets its antimatter counterpart, they annihilate in a pure flash of energy. So why did one form of substance survive to build the cosmos, while the other all but vanished? This is the mystery of baryon asymmetry, and its solution may be hidden within the chaotic moments following inflation. The universe's incredible expansion set the stage, but it was during the subsequent reheating, when the inflaton field decayed and released its energy, that the cosmic dice were loaded. For matter to win out, three special conditions had to be met, known as the Sakharov conditions. The universe had to be out of thermal equilibrium, a state of violent, seething change exactly like the end of inflation. It needed processes that treated particles and antiparticles differently, violating something called CP symmetry, and it needed a mechanism that did not conserve baryon number, essentially allowing the total amount of matter to change. The intense energy of the reheating era could have provided the perfect crucible for all three. Speculative theories suggest that as the inflaton field oscillated and decayed, it could have interacted with other exotic fields in a way that preferentially produced quarks, the building blocks of protons and neutrons, over antiquarks. It is like a cosmic factory with a broken assembly line that only stamps out right-handed gloves, with the left-handed ones being systematically destroyed. For every few billion annihilations that occurred in the hot plasma, a tiny 1 part in a billion excess of matter particles survived. That minuscule surplus is all that remains. The rest vanished in a storm of mutual destruction, and their energy became the background glow of the universe. We are the leftover ash from that colossal fire. The enduring puzzle is identifying the exact physics that caused this bias. Was it a property of the inflaton field itself, or did it happen through its interaction with other heavy, unseen particles that decayed asymmetrically? The answer is written into the fact that we are here at all, a silent testament to a broken symmetry in the first moments of time. That tiny surplus of matter is not the only invisible relic from the dawn of time. The very same cosmic furnace that forged the particles we are made of may have also cooked up the most elusive substance in the universe, dark matter. This brings us to a profound and speculative mystery. Could the nature of dark matter itself be a direct relic of the inflationary era? We know dark matter exists because of its powerful gravitational pull on galaxies, yet it remains completely invisible, refusing to interact with light. Its origin is one of cosmology's greatest puzzles. A compelling theory suggests that dark matter particles were born in the chaotic aftermath of inflation, during the violent reheating phase. As the inflaton field collapsed, shaking loose its immense energy to fill the universe with a hot plasma, that energy might have condensed not just into the familiar protons and electrons, but also into stable, massive particles that simply do not interact with electromagnetic force. Two leading candidates for this primordial substance are WIMP and actions. WIMP, or weakly interacting massive particles, are theoretical heavy particles that could have been produced in great numbers as the universe cooled from its incredible post-inflation heat. Think of the reheating phase as a cosmic lottery where the energy of the inflaton field is cashed in for a vast zoo of particles. Among the winners were the quarks that built us, but also, perhaps, these shadowy WIMP, which then simply drifted through the newly formed matter, never to interact with it again except through gravity. The other candidate, the action, presents an even more direct link to inflation. Actions are predicted to be incredibly light, wispy particles, more like a pervasive field than a discrete object. They are so light and weakly interacting that they could have been produced in vast numbers by the oscillating inflaton field itself, a kind of quantum humming that was frozen into the fabric of space as the universe expanded and cooled. The specific properties of dark matter, its abundance and how it clumps together, are like a fossil record from that first fantastic second. If dark matter is made of WIMP, it tells us that the reheating process was hot enough and violent enough to create such heavy particles. If it is made of actions, it points to a deep connection between the inflaton field and other fundamental forces, a connection that might even explain why the universe has so little antimatter. The gravitational seeds planted by inflation grew into the cosmic web of galaxies, and dark matter provides the invisible scaffolding for that entire structure. So when we map the distribution of galaxies today, we are indirectly mapping the gravitational influence of a substance that may have been created in the same primordial event that created everything else. The search to identify dark matter is, in a very real sense, an archaeological dig into the final moments of the cosmic inflation era, a quest to uncover the hidden half of our cosmic inheritance. That microscopic seed for an entire galaxy forces us to confront a question that lies at the very boundary of physics and philosophy. Was the first quantum fluctuation, the one that grew into the Milky Way, a truly random event, or was it the inevitable outcome of a hidden, deeper law? We are peering into the moment where causality itself may break down. In our everyday world, events have clear causes. A ball rolls because a child kicked it. But at the quantum level, this chain of cause and effect dissolves into pure probability. Particles pop into existence for no reason at all, their appearance governed by chance. If this fundamental randomness is the final word, then the initial speck that became our galaxy, and by extension you and me, is the product of a cosmic dice roll. There is no deeper reason for its specific location or its exact density. Our entire cosmic history rests on a foundation of ultimate chance. This is a deeply unsettling idea for a universe that otherwise appears so orderly. Yet, what if this randomness is only an illusion, a consequence of our ignorance? The theory of quantum gravity, which we do not yet possess, might reveal a deterministic engine operating beneath the quantum haze. Perhaps at the unimaginably small Planck scale, the behavior of spacetime and fields is not random, but is dictated by a strict, hidden set of rules, much like the intricate gears of a clock ensuring it always tells the correct time. In this view, the fluctuation that seeded our galaxy was not a random accident, but the only possible outcome given the prior state of the cosmos. The challenge is that any such prior state pushes us to ask what came before it, leading to an infinite regression. Did the universe have a first cause, an uncaused cause that set everything in motion, or is the chain of causality eternal and unbroken? The answer, if it exists, is locked within the theory of quantum gravity. Finding it would tell us whether our universe is the result of a cosmic lottery or the only possible universe, unfolding with a beautiful, predetermined necessity. The origin of that first quantum jitter remains the ultimate mystery, the silent, singular event from which all of reality blossomed. This cosmic blueprint, for all its statistical perfection, holds a few defiant blemishes. Across the vast map of the ancient sky, scientists have found strange, large-scale anomalies that refuse to fit the simple story of inflation. The most famous of these is known, rather dramatically, as the axis of evil. It sounds like a supervillain's plot, but it is a genuine cosmic puzzle. When researchers analyze the pattern of hot and cold spots in the cosmic microwave background, they expect these fluctuations to be randomly oriented, pointing in no particular direction. Yet, several of the largest features appear to be oddly aligned with each other, and, even more strangely, with the plane of our own solar system. It is as if the universe's oldest fingerprint has a set of ridges that all strangely line up with our local neighborhood. This is deeply unsettling. Why would the grandest structures in the cosmos, imprinted at the very beginning of time, have any correlation with something as insignificant, on a universal scale, as our solar system's orientation? The most likely explanation is that this is a statistical fluke, a cosmic mirage. When you have a vast amount of data, some patterns will appear significant just by pure chance. Or it could be an observational artifact, a subtle contamination in our data caused by something within our own galaxy that we have not fully accounted for. But the possibility that keeps cosmologists awake at night is that these anomalies are real. If they are not a fluke, then they are a direct challenge to our simplest models of inflation. A perfectly random, featureless inflationary field should not produce such large-scale alignments. Their existence could be a hint of pre-inflationary physics, a fossil from a time before the Big Bang. Perhaps the universe was not perfectly symmetric before inflation began. Maybe there was a primordial structure, a kind of cosmic grain, that inflation stretched but could not completely erase, leaving a faint directional imprint on the entire sky. Alternatively, it could point to a more complex inflationary scenario, one where multiple fields interacted or where the inflaton field itself had a preferred direction, turning the universe's expansion into something slightly more textured than a simple, uniform balloon inflation. These anomalies are the cosmic equivalent of finding a few words written in a forgotten language on the first page of a history book. They might be meaningless scribbles, or they could be the key to understanding everything that came before the story we think we know. Their persistence is a quiet, nagging reminder that our map of the beginning is still incomplete, and that the universe may have been a stranger, more intricate place than our simplest theories can describe. These strange anomalies in the cosmic blueprint hint at a deeper loss, a forgetting written into the fabric of the cosmos itself. One of the most profound puzzles in modern physics is what happens to information that falls into a black hole. According to quantum mechanics, information can never be truly destroyed. It may be scrambled, but it is never lost. This principle is called unitarity. Yet black holes evaporate over time, seemingly leaving no trace of what fell in, creating the famous black hole information paradox. Now, prepare for a staggering leap in scale. The same fundamental question applies to our entire universe. The cosmic inflation era might represent the ultimate information loss paradox. During that fantastic expansion, space stretched faster than light. Regions of the universe that were once in causal contact, able to exchange information, were suddenly ripped apart, pushed forever beyond each other's horizons. The quantum information about the precise state of those regions, the specific details of those initial fluctuations, was lost to us. It was carried away by the expanding fabric of space, becoming as inaccessible as information that has crossed a black hole's event horizon. The universe, in its violent birth, may have forgotten its own initial conditions. This challenges the principle of unitarity on a cosmological scale. If true, it means there are fundamental limits to what we can ever know about the beginning of everything. No matter how powerful our telescopes or theories become, there could be parts of the cosmic story that are permanently erased, details about the inflaton field's first moments that are lost forever to the expanding void. This idea forces us to confront a haunting possibility. The uniformity we see across the sky, the very smoothness that inflation explains so well, might not be a feature of a perfectly tuned beginning, but the result of a cosmic erasure. The universe is uniform because inflation stretched it so thin that it forgot how to be anything else, wiping clean the intricate details of its own origin. Are we living in a universe that has fundamentally lost its own memory? Or does quantum mechanics somehow preserve that information in a way we cannot yet perceive, perhaps woven into the very geometry of spacetime? The answer will determine whether the cosmos is ultimately knowable, or if its first secret is that some secrets are meant to stay lost. The smooth, elegant story of cosmic inflation is a powerful one, but it is not the only tale told about the universe's first moment. A quiet scientific revolution is challenging this dominant narrative, proposing that the Big Bang was not a true beginning at all. Competing theories are emerging, each attempting to explain the very same features of our cosmos, like its flatness and uniformity, without invoking a period of inflation. One of the most compelling alternatives is the bouncing universe model, a concept we touched on earlier. This idea suggests our cosmos is cyclical, an endless loop of expansion and contraction. In this view, the hot, dense state of the Big Bang was not a singularity, but a moment of maximum compression, a big bounce from a previous universe that had collapsed. The smoothness and flatness we observe are not products of a sudden stretch, but a consequence of the immense smoothing that occurred during the long, slow collapse of the prior cosmic cycle. The universe, having already lived and died countless times, is naturally ironed out by this endless process. Another radical proposal is Sir Roger Penrose's conformal cyclic cosmology. This theory paints a picture of an eternal sequence of eons, each one a separate universe with its own Big Bang and an infinite future of expansion. In the far, far future of one such eon, when the universe has expanded into a cold, empty void containing only massless particles, the concept of scale loses all meaning. At this point, the endless, featureless end of one eon can be mathematically identified with the hot, dense, but equally featureless beginning of the next. The universe effectively resets, with the faint gravitational ripples from the collisions of supermassive black holes in the previous eon imprinting themselves as the large-scale temperature variations in the new cosmic microwave background. How do we possibly choose between these wildly different stories? The battle for the beginning is fought with data. Each theory makes distinct, testable predictions. For instance, while inflation predicts a specific spectrum of primordial gravitational waves, a simple bounce model might predict that such waves are entirely absent. Penrose's cosmology suggests we might find concentric circular patterns in the cosmic microwave background, ghostly imprints of black hole collisions from a time before our Big Bang. Scientists are scouring the data for these subtle signatures, looking for the one piece of evidence that can definitively rule one of these cosmic origin stories in or out. The existence of these compelling alternatives is a sign of a healthy, vibrant science. It forces proponents of inflation to sharpen their ideas, to identify what truly makes their theory unique and testable. The ultimate winner of this battle will not be the most elegant idea, but the one that survives the relentless confrontation with observation, revealing whether our universe was born in a fleeting moment of fantastic inflation, or if it is simply the latest page in an infinite, cyclic story. That ghostly imprint from the quantum world, the one that became our entire cosmic structure, presents a subtle but profound transition of its own. How did the fuzzy, probabilistic nature of a quantum fluctuation solidify into the definite, classical seed for a galaxy? This is the mystery of the quantum to classical transition, a process that blurs the line between two very different sets of physical rules. In the first fleeting moments, the fluctuations in the inflaton field were purely quantum. This means they existed in a state of multiple possibilities, a superposition where a region of space didn't have a single defined density, but a spectrum of potential densities, all coexisting at once. It was a cosmic haze of maybes. For these fluctuations to become the concrete blueprints for galaxies, they had to lose their quantum ambiguity. They had to choose a specific value to decohere. In a lab, quantum decoherence happens when a fragile quantum system interacts with its messy, noisy environment. This interaction forces the system to pick a definite state, collapsing the wave of probabilities into a single, measurable outcome. On a cosmic scale, the incredibly rapid expansion of the universe during inflation itself may have acted as that decohering environment. As space stretched at a fantastic rate, different parts of the quantum fluctuation were pulled apart, becoming causally disconnected from one another. They could no longer communicate to maintain their shared, fuzzy quantum state. Each part was forced into a specific classical value, frozen into the fabric of the cosmos as a tiny but definite variation in density. Yet, the precise mechanics of this cosmic decoherence are not fully understood. We are applying a concept we see in laboratory experiments to the entire universe, and the scale is almost incomprehensible. Did the transition happen instantly, or was it a gradual process? What was the exact trigger? The answer is crucial because it tells us the exact moment the universe went from being a realm of quantum potential to a realm of classical certainty, the moment the ghostly blueprint for your existence became real. This transition is the silent bridge between the weird world of the quantum and the tangible world we inhabit, and we are still struggling to understand how that bridge was built. This strange cosmic forgetting connects to a deeper mystery about time itself. Why does time have a direction? Why do we remember the past but not the future? The answer may be traced back to the very specific state the universe was in after inflation ended. The early universe was born in a condition of incredibly low entropy, which is a scientific term for disorder. This is the past hypothesis, one of the most profound puzzles in all of physics. Think of entropy as a measure of messiness. A broken egg has high entropy. A pristine, unbroken egg in a carton has very low entropy. The natural progression of the universe is from order to disorder, from low entropy to high entropy. And this relentless slide is what gives us the arrow of time. It is why ice melts in your drink, why perfume diffuses across a room, and why we grow older. The baffling part is the starting point. The hot, dense soup of particles created by reheating was in a state of astonishingly low entropy. It was incredibly uniform and smooth, a highly ordered configuration. This is deeply counterintuitive. Why would the universe begin in such a pristine, organized state, poised to create all the complex disorder we see today? It is as if you walked into a child's playroom and found every single toy perfectly organized on the shelves, knowing that in a few hours it would be a glorious mess. The question is, who organized the toys? Cosmic inflation is often proposed as that organizer. By stretching space to an incredible smoothness, it may have effectively wiped the slate clean, creating that uniform, low-entropy initial condition. The violent expansion ironed out any wrinkles and irregularities, leaving behind a blank canvas of extraordinary order. Yet, this solution may only push the puzzle one step back. To start inflating, the inflaton field itself had to be in a very special, high-energy configuration. Was that initial state of the field also one of low entropy? If so, how did that happen? We are left wondering if the arrow of time was an accidental gift from the inflaton field. or if the true origin of cosmic order lies in a realm we have not yet discovered. The universe's relentless march toward disorder, the very reason you experience a flowing time, may have been set in motion by a moment of impossible, primordial perfection. The smooth elegance of inflation's story begins to fray when we demand to know its true identity. We have spoken of the inflaton field as a theoretical necessity, a ghost that drives the cosmic engine. But what is this ghost made of? This leads us to a grand and frustrating challenge: the struggle to unify the inflationary paradigm with a specific model of particle physics. For inflation to be more than a compelling sketch, we must connect it to the known particles and forces that constitute reality. Is the inflaton the Higgs boson, the particle that gives others mass? Or is it a new, exotic particle predicted by a grand unified theory, one that merges the electromagnetic, weak, and strong nuclear forces? Perhaps it is a vibration from the tiny, curled-up dimensions of string theory. The problem is that we have a surplus of potential candidates and a crippling lack of evidence to choose between them. Each candidate, from string theory landscapes to grand unified fields, predicts a slightly different version of inflation. One model might suggest the expansion lasted a little longer, another that the quantum fluctuations were a bit stronger. These subtle differences would leave distinct imprints on the cosmos, like different artists signing their work with a unique flourish. Yet when we look at the universe, the data we have from the cosmic microwave background is not yet precise enough to point to one signature and rule out all the others. It is as if we have a room full of people who all claim to be the artist, and our only way to identify the true one is by a single, blurry fingerprint that they all seem to share. This is more than a technical obstacle. It strikes at the heart of whether we can ever have a complete and testable theory of the early universe. Without identifying the inflaton as a real particle, the entire framework of inflation risks remaining a beautiful but ultimately untethered mathematical story. The quest to find this particle is a hunt for the single most important actor in the cosmic drama, the entity that literally shaped everything we see, and whose true nature remains one of the most profound and elusive secrets of our existence. The fate of cosmic inflation rests upon a whisper, a signal so faint it has eluded our finest instruments for decades. Our final mystery is not one of the ancient past, but of the immediate future, a question of ultimate testability. Can we ever find definitive proof? The next generation of cosmic observatories is being built with one primary goal: to hunt for the primordial gravitational waves generated by inflation's violent tremors. These are not mere upgrades, they are leaps into a new realm of precision. Projects like the Lightbird satellite, designed to launch into the quiet of space, and a suite of next-generation telescopes stationed at the Earth's most remote and dry locations, like the high Antarctic plateau, are our new ears to the cosmos. Their mission is to stare deeper into the cosmic microwave background, that ancient afterglow, searching for the specific twisted pattern in its polarization known as B modes. This pattern is the unique fingerprint of gravitational waves rippling through the fabric of the infant universe. The challenge is monumental, as this signal is billions of times fainter than the already subtle temperature variations we have mapped. It is like trying to detect the microscopic ripples from a single raindrop that fell into a vast ocean at the dawn of time, after the waves from all subsequent storms have crisscrossed the seas. These new instruments will employ armies of supercooled detectors to filter out the contaminating noise from interstellar dust and galactic synchrotron radiation, peeling back the layers of cosmic static to see if the primordial signal is truly there. But what if they find nothing? A definitive non-detection would be just as revolutionary, forcing us to abandon simple models of inflation and compelling a radical rethink of the universe's first moment. The entire theoretical edifice, for all its elegance and explanatory power, hangs in the balance. The future of cosmology is a high-stakes wager, a bet that the universe left a detectable calling card from its birth. We are building the machines to read it, and the answer will either confirm our grandest cosmic story or send us back to the drawing board in search of a new genesis. From the trigger that ignited a fantastic expansion to the ghostly quantum seeds that blossomed into galaxies, we have journeyed through 25 profound puzzles. We confronted the graceful exit that birthed the hot Big Bang and the hunt for primordial gravitational waves, those faint echoes of creation. We saw how the horizon and flatness problems reveal a cosmos balanced on a knife's edge, and how the missing monopoles hint at a reality stretched unimaginably thin. The multiverse hypothesis expanded our vision to an infinite cosmic foam, while the nature of the initial singularity questioned whether time itself had a true beginning. We wrestled with the measure problem's infinite probabilities and the staggering cosmological constant problem, the largest mismatch in all of science. The trans-Planckian dilemma reminded us that our story rests on a foundation we have not yet discovered, and the fine-tuning of fundamental constants asked if our universe is a cosmic fluke. We explored the search for non-Gaussianities, the statistical ghosts in the machine, and the terrifying instability of the false vacuum, the origin of matter's dominance over antimatter, and the potential inflationary birth of dark matter connected this ancient era to the very substance of our existence. We pondered the ultimate randomness of quantum causality and the strange, large-scale anomalies that defy our simplest models. The paradox of cosmic information loss questioned what the universe has forgotten forever, while competing theories of bouncing and cyclic cosmologies challenged inflation's very throne. We saw how quantum possibilities solidified into classical reality, and how the arrow of time itself may be a gift from inflation's low-entropy beginning. Finally, we faced the ultimate challenge of identifying the inflaton field itself, the ghost in the cosmic machine whose true identity remains the grandest secret of all. This brief, fleeting moment, a fraction of a second in the life of the cosmos, holds the keys to understanding everything from our origin to our ultimate fate. Each of these 25 mysteries is a thread in the grand tapestry of reality. So we turn this final question over to you. Which of these cosmic enigmas captures your imagination the most? Is it the haunting possibility of the multiverse, the search for the first gravitational whisper, or the mystery of what, if anything, came before? Share your thoughts and continue to look up with wonder, for the greatest discoveries on the frontiers of cosmology are still waiting to be